All right, let's have a look at this thermal expansion problem here. We're given two objects. One is a lead sphere and the other is a steel ring. We're told that the lead sphere is a little bit bigger than the steel ring at some initial temperature T naught. And then we're asked at what common temperature will the ring just slip over the sphere. So basically we have this system of a sphere and a ring, and they're going to be in the same environment. So we want to know what is the temperature at which they will fit together. This seems like a random problem. It's an important concept, though, the idea that you can have components that are made of different materials, and those components are going to be in the same temperature environment together. So as they expand at different rates with respect to temperature, you need to take that into consideration when it comes to your design and what materials, not just like what your design looks like on paper, but what materials you're going to be using to put together when you actually bring that design into the real world. So this is an example of that. We're going to assume that we are given the coefficients. I'm going to let the coefficient for lead, we'll call that alpha sub L for lead, and then steel, we'll call that alpha sub S for steel there. Okay, so we got to take some of this information and write it algebraically as we commonly do with physics problems. So one of the important things that we're told here is that the lead sphere has a diameter that is, we're given the percentage, larger than the steel ring. Okay. So in my experience, students see this and start to panic a little bit when they see that percentage. And remember that this is a percentage that it is larger, right? So I want to give you a moment, kind of think about how to write out that statement. But and then I'll show you, there's more than one way to do this, but I'll show you how I'm going to express it. So the initial diameter of the sphere, so we'll say sphere initially. So that means at this initial temperature, T naught. I could say the diameter of the sphere, let's see, I'm using S for steel, so I'm not going to I'll use D, I'll use 1 for the sphere there, is equal to the diameter of the ring, right, plus a little bit. Plus how much? Well, plus that 5/100ths of 1%, right? So if we're going to write a percentage into a decimal, if you don't know how to do that, please review that. That's really important to be able to do. I'll do that. 5 times 10 to the negative 4, that's how I would write that percentage as a decimal. Okay. So the diameter D1 is the diameter of the sphere, right? And D2 is the diameter of the ring. Okay. Initially at T naught. So if the sphere and the ring are just supposed to fit inside each other, the condition we want, so I'll say here, what we want is we want the sphere plus whatever change that happens in the sphere to be equal to the ring, the initial, right, plus whatever change happens to the ring. So basically this quantity here is like the final diameter of the sphere. This quantity here is the final diameter of the ring, right, at the new temperature. Okay. So now we can handle that because we know about thermal expansion. So I can write the change in diameter of the lead sphere is going to be equal to alpha of lead times the initial diameter of the sphere times the change in temperature. The change in temperature is going to be the same for both components, right? Because they're together. The change in diameter for the lead ring is going to be equal to the coefficient for steel, for the steel ring, the coefficient for steel, the initial diameter of the steel ring times the same delta T that I have over for the expression for the sphere. Okay, initial and final temps are the same. Great. So I can then substitute those deltas into the line before there into our constraint condition. So I'll have sphere initial diameter plus, now this expression for delta D1 is equal to ring initial diameter plus the change that the ring will undergo when we change it to the new temperature. Okay, now something that you might not know, maybe if you look these up, whatever, but an interesting little tidbit here is that the change in lead, the alpha value, the coefficient, I should say, for lead is appreciably greater than the coefficient for steel. So what that means is with any change in temperature, the lead is going to change more than the steel. So the first conceptual question that we can answer by knowing this is, do we have to heat or cool the system? And because the alpha value for lead is greater than that of steel, we see that we have to cool the system. If we heat it up, then the lead ball is just going to get larger at a larger rate with respect to temperature than the ring will, right? So we have to cool it so that we can take advantage of that greater change and get to the point where the sphere is at the same diameter as the ring. That's the constraint we're being asked for in this problem. Great. Now we can solve for delta T here. So I'll just isolate my delta T. Let's see, lead sphere minus steel times the diameter of the ring is equal to diameter of the ring minus diameter of the sphere. Okay, and then we can solve for delta T symbolically. Ring minus sphere all over this denominator here. And then you can sub in values from the problem that are given in the problem. And if you look at the written solutions, all the numerical values are subbed in. And what you end up with solving for with delta t is you end up getting negative 29.4. Actually, this is not degrees Celsius, this is Celsius degrees. So yeah, it's exactly what we expected. So I think it was important to kind of explore this question of, do we need to heat or cool the system? That's a good conceptual exercise, but also it provides a way for you to evaluate your answer. So if I get an answer that's positive, that wouldn't make sense here. I expect my delta T to be negative. And remember, delta is the change. It's always final minus initial as far as temperature goes. So it can be positive or it can be negative. And then just oh wait, this is a change in temperature actually that we solve for here, and this problem asks us for the final temperature. So actually, I'm not done. So to find the final temperature here, final temperature is going to be just the initial temperature plus some delta T there. So initial temperature, if we're given that the initial temperature, I guess in the numeric version of this problem, the initial temperature is given as 70 degrees Celsius. So our numeric answer for final temperature then is going to be 70 degrees Celsius minus 29.4 Celsius degrees. That gives us 40.6 degrees Celsius. So this is our final temperature. So this is the target temperature for which the ring will fit over the sphere. So I'm just going to pause for a moment and tell you that the Celsius degrees Celsius thing, students are sometimes confused by this, but it seems finicky, but it's kind of important that we use Celsius degrees when we're talking about a change in temperature, not an actual temperature. So for instance, this 29.4, this negative 29.4, nobody's talking about anything being at negative 29.4 degrees Celsius, right? We're not ever in this problem referring to this as an actual temperature. How we're referring to this is as a change in temperature, only as a delta, right? So that's why technically, and I won't mark you down for this, but if you, as you're moving forward, basically, if you want to have like top-notch notation, then I would say try to pay attention to that. It can remind you also of when you're talking about an actual existing temperature and when you're talking about just a change. And remember that change, that delta, can be anywhere in the temperature scale. That's the Celsius degrees, whereas degrees Celsius is a location on the temperature scale. Hopefully that makes a little more sense. Um, anyhow, if you look at the written solutions, then you will see all the details for the both the symbolic and the numeric version of this problem.